Okay, we have introduced smooth patch and piecewise smooth patch and their length. Now we consider a special parametrization of a patch. Suppose gamma is a piecewise smooth parametric patch. Piecewise smooth parametric patch. Then we have a continuous function sigma. Sigma is a function defined in this way. Sigma t is the integral of from a to t. Maybe not t here. Maybe tau. Okay. So what's this? Now this is our curve. This is gamma a. This is gamma b. Then this is gamma t. From the formula for arc length, we know that the sigma t is the length of this part of the curve. This part of the curve, the length of this part of the curve is sigma t. Okay, so this is the geometric meaning of this function. So this function is piecewise differentiable. This function is piecewise differentiable. Why? Why it is piecewise differentiable? From calculus, we know that as long as the integrand of this variable upper limit integral is continuous, then this integral sigma t will be continuous. So that is if this function is continuous. Maybe I will not write in this way. If map tau to, if this function, the value of the function at tau is the norm of the derivative of gamma at tau, is continuous at t naught, then sigma is differentiable at the same t naught. This is a basic result in calculus. Okay, so because our gamma is piecewise smooth, that is, except finitely many points along the curve, except this finite point, the red dot pointer I select in the picture, except this finite many points. At other points, this function is continuous. Therefore, correspondingly, sigma is differentiable at those points. Okay. Therefore, this sigma is piecewise differentiable, and obviously, the derivative of sigma is the norm of the derivative of gamma at t. So this is positive. So in our definition of smooth or piecewise smooth patch, we require that the parametrization has no zero derivative. So gamma dot t, the derivative of gamma at t is non-zero. Therefore, its norm is positive. Gamma is a map to Rn. Therefore, gamma dot t is a vector in Rn. That is the tangent vector of the curve at the point gamma t. Okay, so this is a non-zero vector, or no. So the norm is positive. So that is sigma. This function sigma defined over the interval ab. the derivative of this function is positive except at finitely many points in AB. Here is the interval AB. So except these finitely many points, at other points, the derivative is positive, and the sigma is continuous. So we can, using from the result of calculus, we know that sigma is strictly increasing. This is the result we want for the previous argument. So sigma is strictly increasing. This is our purpose. So it is strictly increasing. Therefore, if the value of sigma at the point B is L, so this L is precisely the length of our curve gamma, right? This L, that is the value of sigma at t equal to B, is the length of our parametric path gamma. So if L is the value of sigma at B, then we have a piecewise smooth, how to say, we have a piecewise smooth parametric path. Piecewise smooth parametric path, denoted by alpha. Then this alpha is the composition of gamma and the inverse of sigma. Why we can write the inverse of sigma? Because sigma is strictly increasing. It is a strictly increasing continuous function. Therefore, it has a inverse. Okay, it has an inverse function, and also this inverse function is also strictly increasing and also piecewise differentiable. Okay, the differentiability is a consequence of the inverse function theorem. So this alpha defined on the interval 0 L to Rn. This alpha. So this alpha is another piecewise smooth parametric path. Let's study the relation of this alpha and our gamma. So this is the interval A, B, and our gamma is a map to Rn, and this alpha, this is 0, this is L, so this is the sigma. Sigma is 0. Sigma is 0 when A equal to 0. Sigma is L when t equal to B. Okay, so our alpha is this curve. Our alpha is this red one. This is the alpha. So alpha is the position of gamma and the inverse of sigma. The inverse of sigma is here. Okay, so this alpha and the gamma has the common image. So they are the different parametrization of the same curve, same patch. So both gamma and alpha are parametrization of the same curve. C is the image of gamma, also the image of alpha. But the domain of definition of these two parametrization are different. Okay. So this alpha is what we said parametrized by arclength. The curve alpha is a parametrization of C by arclength. alpha is parametrization by arclength. Okay, why it is parametrization by arclength? We compute the we explain why such alpha is called parametric by arclength. Okay, geometrically this means that the length of this part is precisely as we prove this result in the next page. So remember, alpha is the composition of gamma and the inverse of sigma. Okay, so gamma t. What we have alpha is the gamma and the inverse of sigma. So this implies that the composition of alpha and sigma is gamma. So by the chain law, alpha prime sigma prime t is gamma prime t. This is a chain law. Okay, then you should not forget that this is a vector in Rn, because gamma is AB to Rn, and also this is also a vector in Rn. Only the derivative of sigma is a real number. Okay, whenever you write a quantity, you should know whether this is a real number or a vector. Okay, now this is an equality of vector. We take the norm. Taking norm, we get alpha prime sigma prime t, the absolute value. Of course, the derivative of sigma is positive when it exists. Therefore, the absolute value is not necessary, but it is not better to write this absolute value. Then this is equal to norm of gamma prime t. Okay, this means because our sigma t, remember our sigma t is given in this way. Therefore, sigma prime t is the gamma prime t. Okay, we have this. So from this and this, we conclude that the norm of alpha prime s, that is alpha prime sigma t, is 1. Therefore, the length of the curve from 0 to s is the integral of 0 to s derivative of alpha c d c. So this is precisely s. So that is using the new parameter s. The s is precisely the length of the curve from the starting point to the point alpha s. So this is why we called alpha the parametrization of the same curve gamma by parametrized by arclength. Okay, so from this result, we also know that the left hand side is 0s. Okay. I already write here. So from this result, we're taking derivative on both sides. We see that alpha prime s is precisely 1. So this means a parametrization is parametrized by arclength if and only if the norm of the derivative is 1. at all but finitely many t. So the conclusion is that gamma AB to Rn may be 0. Maybe we should use 0. 0 B to Rn is parametrized by arclength if and only if the norm is identical to 1 at all but. We don't require this to fulfill for every point in the interval 0b, but we want it can be false at finitely many points. Okay, so this is the discussion about arclength, parametrization by arclength. Okay, now having studied curve so far,